peak is fine. Just weird things like that. You can never figure out these times. Our optical system measures at red, green, and blue wavelengths. That's all this shows. And we have this dye in there that's blue to start with. It looks like that. It turns pink over time. And then a little later, after it gets further reduced, it turns colorless. So the red light is very good at being absorbed by the blue color. The pink color is nicely absorbed by the green. The green light's nicely absorbed by the pink color. And the blue light sort of passes almost with the same small amount of absorbance through both. And so these two let us look at how much of two forms of the dye, the unmetabolized and the metabolized, are present, and this lets us count the cells. And so I think this, I'll show you some data curves again from space compared to the ground. Space flight are the darker curves, ground are the lighter curves. This is the 525 nanometers, so the green wavelength, hence the green curves. And what you're seeing here is the interesting shape of this over time, and this is about 12 hours, is the blue turning to pink. That's this coming up. The pink then turning colorless. It goes back down there. So now the blue's gone and the pink is gone. And then the optical density of the cells, which are still growing, comes up. And that's what's going on here. So it's an interesting shape. It's very characteristic, and you know this isn't some weird temperature effect because, first of all, it does the same thing in space and the ground. Again, the space growth is delayed a little slower than on the ground, but it basically does the same thing. The mutant looks a little different from the wild type. In this case, the mutant is a radiation-sensitized mutant, so it's more susceptible to space radiation. And I thought, okay, these curves are pretty crazy looking, but interesting. And they're probably different, but you can see the error bars here, the gray sort of things are standard deviations for N of 6 or N of 5.